Yeah, hi everyone. Thank you for coming. Yeah, I know there's been some rescheduling of this talk, so I'm glad everyone made this. And yeah, I'm happy to be here finally. I'm a bit late, but better late than never. So yeah, I'm also a bit rusty. It's been a year since my last talk, so I hope to make it interesting though. So today I wanted to talk about the building blocks of today's and tomorrow's LLMs. And so this talk is a 25-minute talk, so I can't cover everything. But I thought, so the goal of this talk is to catch you up with all the, or let's say the main interesting building blocks of LLMs this year. So what has happened this year? So there's a lot going on, as you know. When you go on social media, on the news, there is almost every day a new LLM, a new method coming out. So I try to focus on the most essential ones. So here in this talk, I will first cover the LLM landscape in 2025, just focusing only on this year, mainly because, yeah, otherwise we would have like a week-long session. So I try to capture the developments in a graphic here. So the main LLMs since earlier this year. I'm cheating a little bit because I'm also having Llama 2 here and DeepSeek version 3 on the left-hand side, and they came out end of 2024. But it's like roughly, let's say, a year from today. And these are also just the most notable LLMs today, the open weight LLMs that most people use from, let's say, Llama and DeepSeek version 3 up to GLM 4.6. Of course, maybe there were already some new models coming out yesterday that I missed, but these, I would say, are the most interesting, most widely used ones. And then I will later on also talk about some alternatives. So this is almost like a very empty slide. I will make it a bit more crowded later on. But yeah, so the main theme this year in terms of LLMs, what LLMs are focusing on in terms of the architecture is making the models bigger. So for example, the trend was almost started with DeepSeek version 3 going to 671 billion parameters, and then Kimi K2 with 1 trillion parameters and so forth, so making models bigger. But then at the same time, people, like more and more people use LLMs, so the focus has also shifted more and more towards how we make them more efficient, like lowering the inference costs to be able to use models with trillion parameters and also using, like having a lot of customers using these LLMs, for example, when we deploy LLMs. So I wanted to introduce some core building blocks. One of them is grouped query attention. So this is an older technique that came out in 2023. This was already used by Llama 2 back then. So it's not a new technique, it's just here as a gentle introduction to some of the motivations of some of the other building blocks. So I highlighted the LLMs that are using grouped query attention here from Gemma 3 to GLM 4.6. So it is still a pretty widely used technique. And where it sits in the LLM, so this is a very crowded image of Qwen 3 LLM. I just picked one of the many LLMs, but the structure of the LLMs is almost always pretty identical. And in the center, we have this transformer block that is repeated a couple of times. And in this transformer block, there's this attention mechanism, multi-head attention, and grouped query attention, or GQA, is essentially an alternative to the standard multi-head attention block. Again, not a new technique, just a gentle introduction to how we can make things more efficient. So on the left-hand side, it is a regular multi-head attention where we have queries, keys, and values. So because it's 20 minutes, I won't go over, let's say, the details of how this is internally computed, what we do with the keys and values and queries. But the message is here that we have a value and a key for each query. And then grouped query attention is an idea. It's like, how can we, let's say, I wouldn't say cheat, but how can we approximate this a bit to make this more efficient? For example, instead of having a key and value for every query, we only, for example, on the right-hand side have a key and value for every second query. So here we are now halving the numbers of keys and values. And the idea is essentially nowadays almost every LLM in inference mode uses something called a KV cache. And the KV cache is caching all keys and values from previous words. So LLMs are generating one word at a time. And to avoid recomputing redundant keys and values that we reuse, we can store them in a cache. And this cache becomes really long at some point if we have these long inputs. So the idea is, how can we reduce the KV cache? And that is by sharing more keys and values among these queries. Just one little trick, basically. And if we do it just right, so we could go to an extreme case where we have only one key and value for all the queries. This would be called multi-query attention. But this is almost too extreme, because then the model will perform worse. It's too much of an approximation. So there is in practice like a sweet spot between how much do we want to share, but also how much do we want to approximate. It's like a trade-off between compute resources and modeling performance, essentially. And so here I plotted this. It's maybe a bit small. So so basically on the y-axis, what we have is the KV cache size in gigabytes. And we want this to be small, basically, to just save costs in inference mode. And so the blue, at the top, the blue line, the graph is the regular multi-head attention mechanism, how much it would cost with increasing sequence lengths. So on the x-axis, we make the sequence length longer, and we can see it becomes much more expensive as we make the sequence longer. And with grouped query attention, there are different hyperparameters, different group sizes. We can lower this KV cache size. So that's one of the many tricks that has been around for almost maybe 2.5 years now. People are using that. It's not a new technique, but it's, I think, a gentle introduction to the idea how we make things more efficient. And so another idea was multi-head latent attention. So this is something that was introduced by DeepSeek version 2. So before version 3, version 2 came out in 2024. And instead of using this grouped query attention mechanism, the DeepSeek team came up with multi-head latent attention. And Kimi K2 is another LLM using that. And so here, this is also the same idea. How can we reduce the KV cache size, but with another approach, basically. So here, what we are looking at is, on the left-hand side, the DeepSeek version 3 architecture. And on the right-hand side is just like, for reference, the regular multi-head attention module, where we have an input. And then for each input token, we have transformation, a query key and value matrix that computes these query key and values. And this is just how regular attention works. We have these 3 weight matrices. In multi-head latent attention, we have 4 weight matrices now. So it sounds like, okay, we are making things more complicated and more expensive by having yet another transformation. But the trick here is, so again, the idea is to reduce the KV cache size. So instead of having these keys and values that we add to the KV cache, we now have in blue in this center here, we have this compressed version, like a latent representation that is smaller. And then we store only this latent representation in the KV cache size. And during inference, when we then generate the next token, we have these additional 2 weight matrices to up-project, to reconstruct the keys and values. It's almost, if you're familiar with the technique LoRa, it's kind of like a similar idea where we have, we project something into a smaller space and then up-project it again. So it's like a little trick to reduce the thing we want to store in the KV cache here, the latent representation. It's like a compressed key and value. And similar, if we look at a chart, similar to grouped query attention, we can bring down the KV cache size with this technique. And I chose the hyperparameters here, so if you would take the previous plot, you can perfectly overlay it, you get exactly the same savings. So I wanted to show this is essentially an alternative to using grouped query attention. Interestingly, you could also combine those two. So you could use grouped query attention and MLA together. I mean, there's no reason why you couldn't. It's two, how people say, orthogonal techniques. You can combine them. And again, it's a hyperparameter, how much you want to compress, how much you want to save. The interesting part, though, is in the DeepSeek version 3 paper, they found, for example, that if you use MLA with a similar compression or similar savings as grouped query attention, the modeling performance will be better. The trade-off is it's a bit more complicated because we have these intermediate states, so you have to rewrite a bit of your inference pipeline because we now have to store this latent state instead of the regular keys and values, but an interesting alternative to the grouped query attention mechanism. Another trick is sliding window attention. So again, the idea is to save costs, also again, reducing the KV cache size. And so here I highlighted also only two models, Gemma 3 and Mistral 3.1. And Mistral 3.1 is not, as far as I know, even really using that. So if you go to the Hugging Face Model Hub, where most companies these days upload their open weight models, and if you go to the Mistral 3.1 model, you will see they have an option for sliding window attention, but it's disabled by default. So there is also, though, a GGUF weight version of that where it is enabled. So it's hard to say whether, personally, I don't know whether they trained with sliding window attention or not. And you can use it, like it's your own choice if you want to use it or not. So what is sliding window attention? So here, it's on the left-hand side, the classic causal self-attention mask of the multi-head attention mechanism, where each token attends to the current position and everything that comes before it. So that's how you come up with this autoregressive causal mask, basically, where you generate one token at a time, but the model can't look into the future. With sliding window attention, it's the same idea, but you additionally restrict how far back the model can look. So you have like a band here where you can say, okay, each token can look back not to the very beginning, but maybe only a certain number of tokens. On the right-hand side, it's 3 tokens. So instead of looking, if we look at the bottom row, instead of looking at all the 6 tokens, we only look at the current token and 2 tokens before it. And so it's again like a trick to reduce the compute cost, but it's again also an approximation. So we are basically trading off what the model can see with computational complexity. Here is a chart where I plotted it again in terms of costs. At the top is again multi-head, the regular multi-head attention mechanism. And then, I don't know if you can see it, but there's a dotted line, the blue dotted line. So they are dots. And you can see this is like the sliding window attention version of this multi-head attention mechanism. And it is saving, again, KV cache storage. And another interesting thing to add here is you can also, again, combine this with grouped query attention, and that is, for example, what Gemma 3 is doing. So in orange here, that's the grouped query attention mechanism, and the orange dotted line is the sliding window attention together with grouped query attention. So it's yet, again, another trick. And I should maybe also say, in addition to that, you usually don't only use multi-head attention or sliding window attention in these architectures. In Gemma 3, for example, they had 5 sliding window attention layers, followed by a regular multi-head attention layer, then again 5 sliding window attention layers. So going back one slide, so most of the time the model has a limited context that the model can see, but some of the layers can see everything. And so in this sense, you can still capture the whole context. And based on ablation studies in the paper, they found that this gives you almost the same modeling accuracy as regular multi-head attention. Yeah, and so I should have maybe included more slides to make this more, let's say, obvious, but it is a 20-minute talk after all, so I try to focus maybe on the main ideas here. And maybe the most important idea of this year, or not, it wasn't invented this year, but the most prominent technique that almost everyone adopted this year is a mixture of experts. So I highlighted in bold all the models that use mixture of experts modules. And so this is, again, another trick to save inference costs. On the left-hand side, I have an architecture that roughly resembles DeepSeek version 3, but I made this up because this is just a regular dense model. So dense means it's not using mixture of experts. And so what I highlighted here, or what this box on the right-hand side is the feed-forward module of this architecture. And the idea in mixture of experts is to replace this feed-forward block by many feed-forward blocks. So in DeepSeek version 3, they replaced one feed-forward module by 256 of them. But so you're making essentially the model larger, but even though you make the model much, much larger, you try not to increase the number of parameters that is used in each inference step. So the idea is during training, the model has now more capacity to take up more knowledge from the training data set, but you still keep the inference cost the same as with the model that doesn't use mixture of experts. So on the right-hand side, even though the model has now 256 feed-forward modules, you only use 9 of them in each step. And so there's a router module, and based on a given token, the router, it's a little multi-layer perceptron. It learns which of these layers to use. And in this case, in DeepSeek version 3, they used one shared expert that is always active, plus 8 that are selected. So the idea of the shared expert is to avoid learning redundancy. So, for example, the expert might learn how to process or how to interpret language, for example. And so in this case, if you have a shared expert, you avoid each other expert to relearn the same knowledge. And the other experts, they can specialize. Maybe one expert is more geared towards code tasks. One is more geared towards, let's say, Spanish. One is more for math. It's implicit, so it's not like an explicit expert that is only doing coding, but the idea is essentially that the router can decide, given the task, what to route for. And in this sense, we can increase the capacity without increasing the inference cost. For example, in the bottom right, the numbers here are in DeepSeek version 3, we have 671 billion parameters in total, but at each inference step, only 37 billion parameters are used. So it's 20 times less of the parameters are used than are available. So the main idea, basically. And here, I did another plot. For example, the straight line, the horizontal line here, that's the active parameters in each inference step for the dense layer, and also basically how many, let's say, how many parameters this model has. But then if we use mixture of experts, we can see we reduce the number of active parameters the more experts we have, basically. So it's like an idea, if we have a fixed number of experts that we use, 8, but we increase the number of experts in total, we bring down the number of active parameters. So it's one of the most widely used techniques this year. So I realized, so this is only a 20-minute talk, so we can't go into all the nitty-gritty details in terms of ablation studies and different design choices and everything. But I have a blog article where it's probably too many words, maybe 8,000 to 9,000 words, where I was elaborating a little bit more with figures and numbers and paper references. So if you're interested, I also made a short link ahead of AI.com, which just forwards to my blog because that's easier to spell than my first and last name. So yeah, if you want to read more about these different architecture designs this year, you can find out more in this blog post. And yeah, in the talk abstract that I submitted to the PyTorch conference, I also mentioned I wanted to briefly mention some other alternative architectures. So far, we covered broadly these models at the top. These are the conventional decoder-style transformers. And today, if I were to implement an LLM for an important application, even like a chatbot for a customer, I think my go-to would always be one of those models still. They also come in different sizes because they are the ones that so far stood the test of time. They perform very well. And you have a range of different model sizes. So that's something I would always consider as the first thing. And then if you are feeling like, oh, I should do some experiments, I should compare it to some other models, maybe make things more efficient, make the accuracy better. There are some interesting developments that are maybe worth taking a look. They're very experimental at this stage, but I'm just saying there are people working on things that are not these classic decoder-style transformers I just talked about. So for example, just off the main branch, there are a few flavors now that are very similar. So they're still decoder-style transformers, but they have a few tweaks. For example, Qwen 3 Next is a model that uses a gated delta net. And I think in every other, or it's a 3-to-1 ratio layer where they have a more efficient alternative to the attention mechanism, for example. Or DeepSeek version 3.2 experimental is another architecture that came out recently where they use a sparse attention mechanism. And the idea, I mean, the models work the same as the other ones, except they are even more efficient. So they're trading off some absolute modeling accuracy by making things more efficient by approximation. So these are some that recently emerged, Qwen 3 Next and DeepSeek version 3.2. I also was tempted to put DeepSeek OCR on there, but it's not really, I would say, an attention hybrid model that would fit in here, but it's another interesting development, more like for research purposes though. Another hot topic was basically the hierarchical reasoning model. And so this made a big splash because it achieved really good performance on this ARC benchmark. It's basically a puzzle, almost like an IQ test, these types of puzzles where you have to arrange blocks given some examples. And there was recently a new version of that, or like a simpler and more efficient version called Tiny Reasoning Model. And this also, it was a very, very popular model that was discussed everywhere. I think it's a really cool direction, but one thing I wanted to highlight is it's something worth looking into, but it is not a language model in that sense. I mean, it's a transformer, but it can't parse language, at least not yet. It's more for puzzles, special purpose. And I can see these models being used at some point as part, like as part of other models, when you do function calling, when you have an LLM and you want to solve a specific problem, you can use a calculator, you can use a search engine, and I can envision these tiny reasoning models, hierarchical reasoning models, being like one of these models that are being called as part of an ensemble of other models, basically. World models. So world models started out with, or in the vision domain, computer vision domain, basically. But there was one model, I think it was earlier this year even, code world model, I think it was by Meta. And this was also a very cool approach where the idea here was essentially, instead of just training a code model, so world models are simulating the world as they see it or process it. In a sense, it's like an abstract simulation of, let's say, a physical world. In this case, it would be specific to code, where instead of just doing next token prediction, the model also looks at code traces. So if you have code, you have intermediate variables and so forth, the model also learns those. It adds a bit more complexity during training, but the paper was very promising. It's a very new approach. I think there's only one model out there right now, 32 billion parameters. But this is, I think, I would bet it's one of the more interesting ones to pursue. It adds more complexity, but I think it looks very promising to make, let's say, transformers better on coding tasks even. Text diffusion models, also a hot topic. So there were lots of papers this year on text diffusion models, an alternative to the autoregressive language modeling. So instead of generating one token at a time, text diffusion models, they generate all the tokens at the same time, essentially. But then there are iterations, like you probably know diffusion models from Stable Diffusion. This was like a company, and they developed open weight models that made diffusion models popular a few years ago, where you have an image and then you denoise the image. And this is the same idea for text, except that text is discrete. Without having a figure here, I think the easiest way to think about it is if you are familiar with masked language modeling, like in BERT, the B-E-R-T, BERT model. It's you're masking out tokens, and then you're trying to reconstruct it. And you do it in this diffusion case, you do it then multiple times. It's like doing BERT multiple times with this masking. You generate all the tokens at the same time, which is great because it sounds like, okay, we are now parallelizing the text generation, which is usually pretty slow in large language models. But then the downside is, for example, you wouldn't be able to take advantage of things like reasoning, where you have a reasoning chain that can enhance the modeling performance because you are generating everything in parallel. I realize I only have 1 minute left, so I wanted to just highlight a few others. Liquid foundation models based on partial differential equations, transformer RNN hybrids. There was just a new RWKV paper. It's like an RNN transformer hybrid. And then, of course, all the state space models. It's also a very important, interesting direction that the state space models coming from pure state space models are kind of being more hybrids now, also with our attention mechanisms. So yeah, there's a lot of interesting stuff going on. Also, even LSTMs got new revisions, like XLSTM, which is not quite as good as transformers, but is very efficient for example, on-device applications. So each of those could be essentially another 20-minute talk, maybe 2-hour talk. So I don't want to keep you too long because I have. Oh yeah, yeah. So I wish though I could. I mean, I was planning with 25 minutes. I had then more figures and images. So, but I think yeah, this is just highlighting the ecosystem, the LLM ecosystem this year, and all the interesting alternatives that are being developed. Like I mentioned before, personally, I would still start at the top with one of those models, and then if you are experimental, you know, looking a little bit beyond the usual suspects, there's a lot of also interesting other work going on. Yeah, and so I was planning to also write this up nicely as maybe a longer article because, yeah, it's only a 20-minute talk. So maybe in the upcoming weeks when I'm back home in my office, I will work on writing a blog article. So keep an eye out where I will go into more detail in terms of how these other modeling variants work. I wanted to say also the PyTorch conference is organizing a book signing session and yeah, has a bunch of books here on site. So I'm honored to be invited to sign them. So if you are around and you are interested in yeah, a copy of my book, Build a Large Language Model from Scratch, it will be in the Expo Hall at 3:20 p.m. So maybe a bit earlier even, let's say 3:10, 3:20 p.m. I will be there signing a few books if you are interested in that. So the book is about building a large language model from scratch, a very small language model, but it is capable. It's a real language model, the same architecture that I showed you. It's like to basically understand really how it works because, yeah, building something is, in my opinion, the best way to make sure you understand compared to just looking at images. Doing the actual work in code is the real thing, basically. I'm also working on a new book, Build a Reasoning Model from Scratch, which is essentially a sequel of the previous book. It works as a standalone book, but is essentially starting with a pre-trained model and then implementing evaluation methods, inference scaling, and reinforcement learning for building reasoning models. So if you're interested, it's currently also available in this early access program here at Manning. So yeah, if you are interested in something to read after building a large language model, how to make it better on reasoning, yeah, keep an eye out for that. And with that, yeah, this is everything I had for today. I think we have a few minutes for questions if the organizers don't kick me out here. So yeah, thanks everyone for attending, and I will also be around and later at the book signing session. So yeah, thank you everyone. Yeah, so the question is how I see the training stack being different from the inference stack and then from the reasoning stack. I think, yeah, the training is also getting more complicated, multiple stages, pre-training, mid-training, post-training, lots of things. But in the end, you get a model that you can then use during inference. And the difference is, for example, in inference, you have a lot of additional techniques. For example, the KV cache I mentioned many times before in this talk. This would be something you don't worry about during pre-training, but it comes in then during inference. And then quantization, a lot of different techniques you apply to the model to make it more efficient. Reasoning is interesting because the reasoning, you kind of have to decide where you want to start. You can start in the training stage. You add another training stage, like reinforcement learning with verifiable rewards is the most popular one right now, to make the model into a reasoning model. For example, from DeepSeek version 3 into DeepSeek R1, it's essentially just more training. But then you can also not worry about training at all, and you can do inference time scaling. There was last week an interesting paper based on MCMC that found that with the right inference time scaling, so what they did is something like beam search, but with resampling, you can get the same performance as with reinforcement learning, but you don't have to reinforcement learn then. It's tricky though, because I think which one you want to do depends on what your application is, because you're trading off training time with inference costs. So reasoning is usually making the model more expensive because it generates more tokens or you have more sampling going on. And then if you are a company, you have millions of customers, it might be easier and cheaper to just train the model more and then don't do that much inference time scaling in addition to that. Because inference time scaling, like resampling, adds costs in each iteration. If you're a small lab, though, maybe you don't have the budget to do reinforcement learning, so you do this resampling during inference. So it's like an interesting interplay, and I don't think there's a right approach. It really depends on the context. But yeah, good question, long answer. I hope that answered it, though. Yeah, so I saw the first hand here.
That can be hosted on like edge devices, so kind of like live training, either fine-tuning or just from scratch on the device.
Yeah, so the question is if there are examples of small models that are being trained on device. To be honest, I don't know off the top of my head. So I know, for example, Apple is using these very small models on device, and they have been trained with LoRa. So they have like these LoRa adapters. But I don't think they update them on device. They are just swapping out LoRa adapters. And I mean, there are lots of models that are very small. For example, there's a Gemma 3 version that is only 270 million parameters, and there's mobile LLM by Meta, which are very small. They can run on device, but I don't know any application that updates them on device. So sorry, it's also these days you only really hear about the research papers, which is usually not applications, and the other is rest is usually proprietary information. So I don't know for sure. Yep, good question though. Yeah, you were also raising your hand earlier.
It seems like most of the new architecture motivations, like Qwen, DeepSeek experiments, they're coming from the inference world, especially, and especially reasoning. And so is it like all the new architectures that we're seeing right now? Is it mainly related because we are looking at very long context? I know like the new state of, like most of the architects are now up to like 1 million context length, but what is the context length that we are looking at? And do you see like the attention especially, right? Because will it survive or will we move to pure like SSMs or... So.
Yeah. So the question is so because you had the microphone only for the second half, I'm just repeating, sorry. So the question was basically why there's so much focus on, or that there is so much focus on the inference part now, and does it have anything to do with the inputs getting longer? That was mainly what it was about, right? So yeah, I think it's because more LLMs are going into, let's say, production from pure research, and yeah, you want to scale up the customers, basically, how many people can use the model without, just like melting your GPUs, basically. And then the challenge is essentially the more tokens you have, the bigger your KV cache size becomes, and that's where you want these alternative attention mechanisms. So a lot of people invest into, hey, how can we get the same modeling performance but saving, basically. Like the first stage is always like, hey, let's build the best model. And now that we have a good model, there are two branches. One is making the model even better. So that's one line of the engineering team. And the other part of the engineering team is like, hey, how do we take the model and make it cheaper? I'm not affiliated with OpenAI, for example, but I would say as an outsider, like observer, that the recent models in OpenAI, for example, have been more focused on making things cheaper also. For example, I remember that last year there was GPT 4.5, which was a bigger, more expensive model, but then they went back to GPT 5, which is cheaper. So there's a lot of engineering focus on this, and we don't know what attention mechanism they use. There are lots of variants, and now Qwen 3 Next with the gated delta net or the sparse attention in DeepSeek version 3. So there is a lot of focus. And the other question was, or related, whether state-space models will replace that. I honestly don't, will replace attention mechanisms. I honestly don't think so, because they're more meeting in the middle now, basically. So because, yeah, early state-space models didn't use attention, and then we have on the other side attention, and then they kind of converge. We have these hybrids. So I think it's more going towards this DeepSeek version 3.2 sparse attention, more tricks, basically, I would say. But I don't see full SSMs replacing attention, not yet at least. So, but this is like short time scale, maybe 1 or 2 years, because the attention mechanism just works too well still, compared to anything else. Yeah.
Mine is just a request. I think it's connected to what he asked. Can you just include maybe a blog post on having a fine-tuning done based on the MOE model for, like, let's say, Qwen 335B or something like that?
Sorry, did I understand correctly? A blog post on the mixture of experts?
Yes.
Yeah, this would be an interesting point, because I think the methods I showed you, like sliding window attention, group query attention, multi-head latent attention, you don't really have to change your training pipeline. But with MOE, you have the Z loss, you have other loss terms. So training MOEs is trickier. So it is, you have to make a...
That, but the model doesn't render itself, right? So like basically on the dense model, it does work.
Yep.
The training pipeline does work. But the moment I switch that model to a MOE sort of a thing, then things start breaking.
Yeah.
So I was just looking for some guidance there.
Yeah, maybe one day I have it on my list to train an MOE. So right now I only implemented MOEs, like the Qwen 3 from scratch is the MOE from scratch implementation for inference. But I don't have any blog post yet on training. This is an interesting one. I have it somewhere on my list after the reasoning models.
So it's just a request. Thank you.
Thank you.
When you're making some of these architectural decisions, are there any special considerations over like classical approaches to hyperparameter search?
So you mean essentially when you come up with an architecture, why you would decide to do this certain architecture and not other architectures, like other flavors?
Right.
Yeah, it's interesting. I think, I would say what's a bit different from traditional hyperparameter search in deep learning is that transformers with this large data are more robust to variations. So I would say there's, whether you use GELU or SciLu activations or GEGLU or SWIGLU, or whether you use one or more transformer blocks or whether you use RMS norm or layer norm, it almost doesn't matter that much. It's like tiny differences where I think I would say most developers, they stick with, like they have like almost like a style, like a certain flavor. Where I think Gemma still uses GEGLU or GELU because it was like a paper they had, so they just stick with it. It's more almost like a historic artifact. For example, when I looked at the GPT-OSS paper, the OpenAI open source model, they use, for example, still the bias term, like in the linear layer. So instead of just doing matrix multiplication, they have the weights multiplication plus the bias vector, which is not, I mean, there were a lot of papers saying it's not required, but I think they still use it because they used it back in GPT-2. And I think in GPT-2 they used it because it was just the default in TensorFlow. So it's more like an historic artifact. There are a few things, though, that do make a difference. For example, I mean, unfortunately, people don't share many ablation studies anymore, but the Olmo 2 paper is actually pretty nice. They rearranged the position of the layer norm, so from pre to post norm, but a bit different from from the original transformer. They put it before the MLP. I think I would have to take a look, but they arranged some things, and then also they added QK norm. There are other models like Qwen 3 that also uses QK norm, but they did it, like they explained why, because they saw spikes in the loss without it. So that is the only thing to go by. They basically look at the loss early in training, and then you look whether it spikes or not, and if it spikes or something, you try to mitigate it. Where in traditional deep learning, you would almost finish the run, right? You would finish the run, look at validation, test accuracy, and in LLMs, it's more like almost like early intuition. Okay, this is not worth doing because it's too expensive. Let's cut it off and try something else. I think it's more like even more gut feeling, if that makes sense. Yeah.
Carry over to the different attention mechanisms that you presented, that the overall model ends up being fairly robust to like reasonable inclusions.
Yeah, I think so. Everyone, I would say there was a point, or almost everyone uses grouped query attention because it is basically almost the same as multi-head attention. And Google, I think, still uses sliding window attention in addition. because it's what they've done in Gemma 2, and they don't have an MOE. I think that's, personally, I'm not affiliated, but I think that's still why they have the sliding window attention instead of using an MOE. Everyone else uses MOEs, and they, let's do sliding window attention. That's my, as an outsider, what I would think why they did that. And with multi-head latent attention, there was a figure in the paper where they did compare and say, okay, if we use MLA, multi-head latent attention, instead of group query attention, we get better modeling performance, basically. So there was like a reason in terms of on the data sets they do get better performance. Otherwise, I don't think, I mean, there are other things you could change up. What's interesting is also there have been a lot of these linear approximations to attention for a long time, since maybe 2019 or something. They get proposed in papers, but it never really get used in practice. It's just this year where people like DeepSeek version 3.2 with a sparse attention where it gets traction. Maybe it's because now it reached a point where it's, you know, actual money, where these companies spend millions of dollars, and then it does now make a difference. Before it was, oh, it looks nice on paper, but we are still doing short context. So whether I spend, I don't know, like $50 or $60 for my training run on a small academic project, I mean, maybe more, 500 or 600, it doesn't make such a big difference. But if it's like $50 million versus $100 million, that makes a bigger difference. Maybe what's motivating that basically this year, I guess, yeah. Yeah.
A really short question. So, sorry, you spoke about.
There's the microphone. I was like.
You spoke about diffusion models for text generation, and I'm wondering how these approximate to the discrete space of tokens and text, whereas diffusion models essentially, you know, through noise, you're approximating a continuous space. Like, I think of them as pixels. Is there some way of like almost snapping it to a word embedding or something like that?
When I understand correctly, is how to make it instant, or like how to get the text immediately? Like
no, well, so text is tokens, right?
Yep.
And tokens is a discrete space because every token has a embedding attached to it or some sort of discrete representation. Whereas diffusion models typically have
continuous.
It operates in the continuous space. So like, how does how do you reconcile with that?
I would say it's definitely a different loss in a sense, but I think it's the term text diffusion models is maybe it's suggesting it's using the same pipeline, but I would have, I mean, there are many papers. I will maybe go back and rewrite this up in a blog post more nicely because I have only like glanced at them. But I think it's quite different. It's more like how a BERT model works, BERT, back then when you masked different words and then you're just trying to predict the missing token, basically. You know, like it's more like masked language modeling than anything related to images, basically. And it's in that sense just a chain of these unmasking steps. So you could technically use the same approach as in BERT, basically. That's my understanding. But I will. This is one thing where I'm not an expert in text diffusion models. It's something I focus more on the transformers. But this is something where I will sit down and go through the papers at some point and maybe write up something to reconcile that and compare. Yeah. Yeah.
Can you share your perspective on model chip co-design given all these different model architectures in the last years? So do you think it is necessary or not?
So the question is if I could share my how to let's say how to put them into action, like how to reconcile all these different.
Do you think it's necessary to do the co-design or not? Or
if it's necessary to do the coding, you think, or sorry?
So model chip co-design, and someone are doing the specialized chips and hardware for the models, and but given all these different architectures, and how do you weigh in the trade-offs?
It's so how to like these custom chips. To be honest with you, I mean there are lots of custom chips. I think. I mean, again, I'm not affiliated with any company, so I don't want to say they are good or bad or anything like that, but I think there are, there are different layers where, for example, TPUs are really good at matrix multiplication, basically. I think it's trickier to do other things beyond that. I think different chips have different strengths, and I don't know in terms of, I never worked with TPUs because they are proprietary to Google. I heard they are going to sell them at some point to other cloud providers. But in that sense, you, for example, have specific software that is specific to that chip, and then there's the model on top of that also. And I don't know honestly how specific these chips are for certain flavors of attention. They are mostly about matrix multiplication. An interesting development is, for example, memory bandwidth. For example, I think I don't have the DGX Spark, but that's what a lot of people talked about, where it makes more like of a difference how big your model is. If you have a bigger model, you move less data around. There's more computation than something like that, where you have more flops benefits from a graphics card that has more memory bandwidth. And I think it's more about that at the moment, where, for example, the open weight models like DeepSeek, the developers, they're figuring out how to do things with, let's say, lower end chips or new chips, and how to connect the chips together, basically, in an efficient way. And then maybe this motivated the design of these attention mechanisms, because in that setup, it's even more beneficial. But to be honest, hardware is something that is a bit outside my expertise, to be honest with you. But good question, yeah. Mm-hmm.
Yeah, thanks for your presentation. I wanted to ask regarding explainability for LLMs now, because there's so many parameters. Now we might go to pentat. We are currently at trillion parameters, but we might go further, and they become more and more complex. And in traditional black box model, we used to have like algorithms like Shapley, line to explain. And I think for some reason, I think chain of thought was supposedly a good way to explain. Do you have any insights on like explainability and how we can or is it even useful for LLM world?
Yeah, it's a good question how we explain these models when they get bigger. Yeah, I think it's getting trickier also because it's more expensive. They're getting bigger and so forth, but also like it's almost like for a normal person not even affordable to, most people can't even, so a lot of models are also proprietary, so you can't even look into anything beyond input and output. And even then, it's also very expensive. For example, there are costs like $1,000, $2,000 just to run it on a standard benchmark. And then now imagine you had to do something with gradient approximation or anything like that. It's very expensive. And I think maybe we'll see this more in multimodal language models, but I don't think there's much emphasis anymore on understanding things. It's more in terms of what the internal layers are doing. I think there was an interesting blog post by Claude. They looked into this. They did like a blog post looking into intermediate layers. I read this like last year, I think it was, but yeah, there are like tips and tricks and workarounds, and I don't know how much of that is really reflecting what the model is doing. It's trying to maybe find a way to explain it, but it's tricky. And it's like, yeah, I think what makes more sense almost is to focus on custom evaluation methods, like to relate it to a business problem. How well is the model solving the business problem? Why it is solving the business problem? Well, if it solves it well and it's reliable, I think that's more like the focus right now. And I don't see much work on understanding this, unfortunately, but there might be a lot of work I'm not aware of, though. Good question. I wish I had a better answer, but I think no one has at the moment. So it's I would say a black box in the sense that there are so many layers, but I think also at the same time, though, language models are easier even than other types of neural networks. I personally even find it easier than almost convolutional networks, like looking at a attention mechanism, and it's like the same block repeated so many times and in so many architectures. It's almost the same pattern, like a cookie cutter, where in that sense, this part becomes easier. Yeah, but what the model does, yeah, it's a big model that does a lot of things internally, a lot of numbers. It's hard to, to reconcile this in a human interpretable way, basically, almost, yeah.
Thank you.
Yeah, thanks again, everyone. It was fun. I think we went way over, but it was a lot of fun chatting with you all. And yeah, I will be around again later at 3 in the expo hall. So if someone was planning to go, I would love to chat more. And yeah, enjoy the rest of the conference.